Actually, Professor, I have a question real quick.
Yeah, sure,
You
Daniel.
mentioned that there were certain topics had different potential grades assigned by difficulty. Which order, is there a particular order to them here? I don't
Uh,
see it.
no, I don't, each topic you can actually make it a very difficult experiment too. It's
Okay.
not necessarily say which one is more difficult than, which topic is more difficult than the other.
Okay, so it's based on the experiment rather than the topic.
Yeah.
Okay.
Based on
All right, thank you
exam.
for clearing that up.
But, yeah, but still, it's not absolute. To me, some topic seems like it's a little bit easier to make experiment than the others. Do you agree? So it's hard to say. Equally difficulty. It's depend on the the whatever thing you available to you. Okay, sometimes, and also I think what I really means the difficulty is not only to do a difficult experiment. For example, if some experiment need instruments, need some apparatus. I don't need that. I want you to spend no more than $5 for each experiment. Okay, so in that sense, my focus of the difficulty is on the theory. For example, instead of, okay, I measure the flow, I measure the velocity. So that to me, theory-wise, is very simple. There's no difficulty in that. Okay, but if you can say, hey, I verified for example, Pascal's law. I know I did a hydraulic jack or whatever, and actually I measured the force from the two surfaces. Then to me, theory-wise, it seems like it's more, more complex, and yeah, I really don't want you to rely on the instrument or equipment or whatever. If you can make it using everyday materials in your home, that's good. That's if you can design something to verify theory, then that's good enough. Okay, the due date for the first experiment is Monday, in 2 weeks, right? Let's see. Actually, I think I put it on the it should be,
The
no, sorry,
ninth.
Tuesday on the 9th. Yes. Okay. The other thing I want to announce here is I updated the syllabus. Okay, because we said we won't be able to have the midterm exam, so I reduced the point for the exams from 50% to 40%. Okay, so exam-wise, we'll only have one final exam, which is 40%. And I add 5 points to the video project and the quiz. So quiz is 25, and the video project, it will be 35. So I put more weight on the, projects and the quiz. Okay, then I reduce 10 points on the exam since we only have a final exam. Okay, so it's 40% for the final. Okay, so anything else? Yeah, I guess that's all the announcement today. Okay, quiz 2. I posted the solution. It's very simple quiz, right? Simple problem. I just want to see the procedures, the steps you write it on. Is it correct? Okay, so my TA will grade that quiz, so I don't know how long it will take, but I posted the solution on Moodle, so you can take a look. Okay. Yeah, that's about it. And the quiz, I just want to mention a little bit about the quiz. Quiz doesn't have to be, sometimes it will be unannounced quiz, during the lecture, suddenly I feel I need to ask you a question. Maybe I can make that a quiz. Maybe even unplanned quiz like this. I want to make a lot of quiz. So in case you miss a couple, it doesn't matter that much. Okay, so I don't want to have only like 4 quizzes, 25 points, or 6 points for each quiz. That's a lot, right? I want to make it like at least 15 quizzes in the semester, maybe 20. So you miss one, maybe just 1 point. So no big deal. Okay, so and also average score of the lot of quizzes, probably it will really tell the performance of the semester in terms of the quiz. Okay. Okay, so let's come back to, let's switch to my whiteboard. Let's continue on chapter 3. Okay. Okay, that's what we, okay, did you see the screen, by the way? Good. Okay, that's what we were last time. Okay, we did some theoretical derivation, right? From the, look at a infinitely small element. We derived the hydrostatic equation, actually. Okay, I wanna say, okay, be careful. This is actually the equation we derived. dp dz equal to negative gamma. I circled it here. Okay, this is actually the equation. Okay, what we derive. Basically, it's a very simple differential equation. Okay, so that's equation for the hydrostatic problem. Okay, so what is this? This is a P over gamma H, right? I'm talking about this. I also circled it. This is a solution for a particular problem, like the water in the tank. What is the pressure on the bottom? Okay, this is a, it looks like equation P equal to rho GH, gamma H, right? But actually this is a solution for this particular problem for pressure, okay? And since it's such differential equation, dp dz equal to negative gamma, we can solve it using the indefinite integration. It will become P equals to negative gamma z plus C, okay? This to me is a more general form, more general solution for the hydrostatic equation, okay? It's P equals to negative gamma Z plus C, a constant, okay? So that fit for many different applications, okay? For this particular application, your solution is P equal to rho GH, gamma H, right? So this is a more general form of the solution. So if I rewrite it, I move the negative gamma Z to the left-hand side, okay? I look better, right? So let's start from this. P plus gamma Z equals a constant, okay? That's actually the solution, general solution for hydrostatic problem, okay? C, it's a constant, okay? Don't mind what C is, okay? But that actually, this equation tell you a something, you know, in between the lines, tell you some actually physics of a hydrostatic. You know, in a stationary fluid, okay, you know, in terms of the conservation law, okay, I like a conservation laws, you know, that help me understand problem. In terms of conservation law, you say, hey, in a stationary fluid, the pressure is not conserved, right? Obviously, common sense, pressure is not the same in different locations in the fluid, right? Let's say, still let's use this tank example, very simple. So pressure is different, and the surface has zero pressure, and the bottom has the highest pressure, is that right? So here in the middle have the median value of pressure. The pressure changes with the elevation, with the depths. Okay, pressure is not conserved. It's not the same. But this equation tells you P plus gamma Z, these two terms together in this same fluid, actually, if you add these two terms together, it's conserved. It's a constant. So in other words, in a point here, let's say point A in the middle of the fluid, at a point B on the bottom of the fluid, let's say point C on the surface of the fluid. PA, PB, PC, the pressure are all different on the three locations. But if you include the gamma times the elevation, Z, then on these 3 points, P plus gamma Z is the same. Okay, so I put a z-axis here. Don't confuse with z with the depths. Okay, z start from the bottom. So in the bottom, although has it's the deepest location on B, but the elevation, use this equation, z is 0 on the bottom. Okay, so here, PB has the highest pressure, but the lowest elevation part, which is 0. On the surface, hey, I have the lowest pressure, I have 0 pressure, but I have the highest Z on C point. Okay, so P plus gamma Z, this two terms together is conserved inside a stationary fluid. That's the physics behind this equation. Okay, so is that good? Okay, so we give a name, okay, in the textbook. Well, although that name is not often used, but it doesn't matter. It's called a piezometric pressure. It's confusing you by using this name. People will think this is pressure. Actually, piezometric pressure is P plus gamma Z. Okay, the two terms in the left-hand side of this solution, we call it piezometric pressure. Okay, sometimes in industry, when you go to work, they use piezometric. They talk about piezometric head or piezometric pressure. Just keep in mind, that thing is not pressure. Okay, it's P plus gamma Z. So in other words, if I can rephrase this hydrostatic principle, I can say, hey, in any given stationary fluid, static fluid, the piezometric pressure is the same everywhere inside of this stationary fluid. Okay, so again, it's simplify the sentence by using the piezometric pressure. Okay, we define it as piezometric pressure. It's not just pressure, it's P plus gamma Z. So then in that sense, we can say piezometric pressures are the same inside a stationary fluid. Okay, but what's the value? I don't know, depend on the problem, right? But it will be the same. Okay, everywhere inside one fluid. Okay, stationary fluid. Okay, that makes sense? Okay, so by convention, in industry, people use head. You heard about it, right? Pump head, elevation head, velocity head. They always talk about head. So what is head? Okay, so notice this equation, every terms is in terms of pressure. Okay, see gamma times Z, if you look at the unit, it will be pressure. Okay, P is pressure. Basically, the rule of thumb is in the equation. Every term has the same unit, right? Otherwise, you cannot make an equation. So obviously, the first term is pressure. The rest of the term has to be pressure. So if you use this equation, okay, every term has a unit of pressure. Okay, but in industry, people like to use head. Head is, instead of using pressure, pressure is difficult to feel. Hey, 2.5 psi, what does really means? Okay, people want to use, hey, how high the water will be shooting to the sky. So you use that to represent how big the pressure. So in that sense, if you divide it by gamma in this equation, if you divide the gamma every terms, the equation is still valid, right? You can do that, right? Oh, this is just divided by gamma every term. They turn out to be like this. Is that right? Does everybody follow me? Okay, so gamma is a constant, right? It's property rho g again. So still, this is still a C. C divided by a constant, still a C. Okay, of course, the C value is changed with this C, but in the equation, we use C as representing a constant value. Okay, it doesn't matter. So it still looks like a P plus P over gamma plus C equal to C. Okay, so then this is called pressure head. This is called elevation head. Okay, that's what people talk about. It's a pressure head. What is elevation? Elevation head, just elevation. Okay, pressure head is P divided by gamma. If you look at the unit, P divided by gamma become the length. Okay, so we use a length to represent how big a pressure is. Okay, so the longer, the bigger the value pressure head is, of course, higher the pressure is. But the conversion is just this, P divided by gamma become head. Okay. Then this equation, some people like it better than this, because, hey, look at this. I have a elevation Z there. I could directly put the value there. Okay, so to calculate the pressure head. Okay, so this is a different way to write down the equation, but these two are the same, basically. Okay, so pressure head plus elevation head. Again, we give a name of the two things together. Educated guess, what does this call? Piezometric what?
Head.
Yeah, you're right. Just this is called piezometric head. Combine the pressure head and the elevation head. Okay, then it's called piezometric head. I think we use this more than this. Okay, in industry. Okay, so but the physical meaning. This equation, I spent more time here, right? I'm spent almost 10 minutes on this equation. This equation is very important in hydrostatics. Okay, it's not just the equation, it has the physical meanings about this equation, which said is piezometric head is conserved inside a stationary fluid, which means everywhere, any given point inside the fluid, although they have a different pressure, but they have piezometric pressure, and the piezometric head are all the same. Okay. So that means it's conserved. So use this principle, we can easily calculate one quantities, okay, use this equation by comparing 2 points. For example, here, hey, C and B. Okay, so that's a different way to solve problem. Of course, this one, pressure B on the B is easy. We can use the previous way to solve it. You know, pressure B is gamma times H, right? So this is H. Okay, from the previous time, we already know PB equals gamma times H. Okay, but I'm just trying to show you a different way to solve this problem. Okay, so now we can say, hey, I can compare 2 points, B and C. Okay, since I have an equation, I know the piezometric pressure on B equals piezometric pressure on C. So I have an equation. I can write down the equation, then I can solve for one unknown in that equation. Okay, so how do we write down the equation? Between B and C, you have the hydrostatic principle, right? The piezometric pressure, let's say PZ means piezometric pressure. PZA equals PZ, I'm sorry, PZ, yeah, B, I always try to use A and B, that's fine. PB, B between B and C, right? So this is the hydrostatic principle. Piezometric pressure between B and C are the same, okay? Is that right? Everybody follow me here? This is an extremely simple problem. Of course, you can solve this by using other ways, but you will see difficult problem later. You have to use this principle to solve. Okay, I just want to convey this is the new way to solve problem. So you say piezometric pressure between B and C are the same. Is that right? Everybody agree? Okay, so what is the piezometric pressure on B? Here, right? So piezometric pressure on B is PB, real pressure on B, plus gamma CB. Okay, everybody write like this. Piezometric pressure means P plus gamma Z. Okay, from at any point. So B point will be PB plus gamma ZB. Is that right? Everybody agree? How many of you? How many of us today? It's 15. Okay. I want to all 15 of you fully understand before you leave the class today. Okay. So equals, right? So what is the piezometric pressure on C? Can you say it for me? Anybody? What's the definition of piezometric pressure? This, right? Say it. Anybody?
PC plus gamma ZC.
That's correct. That's correct. Okay. So I just want to finish this thing on this page. Okay. So now let's look at it. Okay, can we solve it? What we want to solve? We want to solve PB, right? Let's see if PB equals to gamma H. Okay. So what we have? What is the PC? Anything zero here in this equation? Let me just have this place.
ZB.
Okay, ZB is zero. Look at this coordinate system. Your origin is on B. Okay, you have to follow the same coordinate system for each problem, right? Is that right, everybody? Be careful. Z is not the depths. Again, that's the coordinates. Okay, she's right. Do everybody agree? ZB is zero. Okay, good. Anything else? Zero?
PC.
PC, we said it's open to atmosphere. Gauge pressure for the atmosphere is zero. Okay, so what does PB equals? What does PB equal? PB equals to gamma ZC. What is ZC? Is ZC given?
H.
Yeah. See, you got the same result as the way you previously solved the definite integration, right? You can directly solve that differential equation to have boundaries, have limits, and you can solve it, right? Here, we don't have to use the integration, right? We just use this hydrostatic principle. Piezometric pressure is the same between 2 points. So you can find 2 points to compare. Okay, write down the equation. Hopefully you know 3 unknowns. You know 3 terms, and then you can calculate 1 term in the equation. 1 equation, 1 unknown, right? So this is the new way I'm trying to convey here to solve hydrostatic problems. You can compare a point to a reference point inside the same fluid. Okay, be careful. If there are 2 different fluids, this equation doesn't stand. It's so obviously it doesn't stand. The different C's for 2 different fluids, right? But sometimes people make a mistake. Okay, has to be the same fluid inside a same fluid. Any 2 points, their piezometric pressures are the same. This is the equation. Okay, is that clear? Any questions? Good, 100%? All 15 of you? Okay, let's look at example, a little bit more complicated example than the previous one. Let's say, hey, I'm still having the tank, but instead of 1 fluid, now I have 2 fluids, water and oil. Okay, let's say which one is in the bottom, which one in the top? Water or oil in the bottom?
Water.
Water should be heavier, right? Oil on top. Okay. Let's say the dimension. Okay, you have 2.1 meter. Okay, the dimension of 0.9 meter. Gamma of oil let's say, I'll give you something more difficult. Right? Gamma of water. Do you know gamma of water? Anybody in the SI unit? What is gamma? Rho G, right? What is rho of water? What is G? So what is gamma water? Anybody? I wanted you to remember that value, okay?
Is it 0.073?
No.
No.
Yeah, gamma of water. So what is the density? Is gamma rho G? Rho times G? What is the density of water? Remember? Now you have to remember something, right? When you do some real practice, you need to remember the fundamental, some basic numbers.
Isn't row 1,000?
Yeah, 1,000, right? It's very easy to remember. Okay. In the SI unit, the rho is 1,000 kilogram per cubic meter. Okay. So what is gamma? What is G then?
981 kilograms.
What is G?
9.81 meters per second.
Okay, 9.81 times 1,000. So what is the gamma? Hmm?
9,810
Yeah,
kilograms.
that's right. Newton per cubic meter. Remember the unit. The force per volume, right? Gamma. Okay. Please remember some of those basic numbers. It's good for you. Okay. When you do the real practical applications, it saves you time. You don't want to get frustrated too much. Too many unknowns get you frustrated. Okay. Okay. So how about oil? Let me give you some difficulty. Okay. Let's say the specific weight of the oil is 0.8. Okay, we introduced that, right? Specific weight. What does the specific weight mean? I'm sorry, specific gravity. The specific gravity of the oil is 0.8. Okay, specific gravity, we use S. What does that mean, specific gravity? Do you still remember? That's the new property we introduced in the class, right?
Is that gravity compared to water?
It's close. Yeah, I know what you mean. I think you know. I know what you mean. It's the ratio.
Yeah, so it'd be 800
How heavy? Yeah, how heavy compared to the water?
kilograms per cubic meter.
800 kilogram. Why is 800
Eight.
kilogram?
Water's 1,000, so that would be
Oh, okay, you mean density, right? Yeah, you're right. So let's say what is the specific gravity of oil? Let's use specific gravity. You're right. Density, 80% of the density of water, right? 800 kilogram per cubic meter. That's correct. So what is specific weight, gamma of oil? We're going to use gamma, right? The previous equation is in gamma, in terms of gamma. Right? Is that right?
7,848 newtons per cubic meter.
Yep. Good. Hey, that's one testing point here, right? That's one knowledge we learned, specific gravity, okay? You're right. So gamma of water times specific gravity of oil then becomes the gamma of oil. Okay, so we find out both properties. Good. Let's find out the pressure in the bottom. What is the pressure here? Okay. So you then multiple ways to do it, of course. Okay. If you never take this class, you still know how to, probably you still know how to calculate the whole thing. You can calculate the weight of oil. You can calculate the weight of water. Okay. So that weight is sitting on top of the surface here. Okay, then you divide it by the surface area. That will be the pressure. Pressure is force per area, right? So you need to find out what is the surface area, or maybe it can be canceled, you know, during the process, whatever. That's the original way. If I had high school physics, I should know how to calculate that, right? Is that right? Everybody understand this, right?
Would it
Basically,
just be gamma H?
yeah, it's just the, yeah, gamma H. But remember, before I introduce, I just want to say, before I introduce the way we calculated, you know, this method we learned today, I just want to make sure that everybody know, physically, common sense, you know how to calculate the pressure. Basically, it's just the weight sitting on top of the bottom surface, the total weight divided by the area. Is that right? That's the pressure, right? If you can weight the oil, you can weight the water. That's the total weight sitting on top of the bottom of the tank. Okay, so the pressure is just basically the weight, total weight, the bottom experience divided by area. Okay, that's high school physics. Okay, everybody should know. But now, here, see, how do we use the hydrostatic principle to solve this problem? Okay, so I said in the previous problem, I need 2 points. This principle, it says on any given 2 points, the piezometric pressure is the same. Piezometric pressures are the same between 2 points, right? So I want to utilize this way. So you have to have 2 points. 2 points inside the fluid, okay? And also the same fluid. You cannot jump between water and oil. Then the hydrostatic principle won't apply, okay? So let's say this is a P1 in the bottom. So you need to find a point in water to compare with P1. Okay, this is a point 1. Which other point you're gonna take? I'm gonna take the surface, point 2. The good thing about the interface on 2 is that's a strategy. You know, I'm just trying to tell you it's easy for you to solve problem. Point 2 belongs to both water and oil. It's on the interface. So this hydrostatic principle between 1 and 2, you know, should satisfy that same water fluid, right? Then you can have another point on the surface of the oil. Okay, point 3. So you cannot directly write the equation between 1 and 3. Oh, since we know 3, right? We know the pressure on 3, do we? Okay, pressure is 0 on 3. We know all the dimensions. Seems like we know everything. The piezometric pressure on 3, we know it, okay? So, but we cannot directly say piezometric pressure 1 is equal to piezometric pressure 3 because there are 2 fluids. You cannot jump 2 fluids, okay? So that's why we needed the point 2 as the middleman, okay? If point 2 belongs to either oil or water, it belongs to both oil and water, okay? It's on the interface. So what you try to do is, hey, let's say piezometric pressure on 3 should be equals to piezometric pressure on 2 in oil, okay? They're different piezometric pressures. One in oil, one in water. The density of oil and water are different. Is that right? Okay, so from this, you probably will be able to calculate the pressure on 2. Do you agree? Then next time you can say, hey, PZ2 will be equals to PZ1 in water. Notice this 2 PZ2 different. I said in water and in oil. They're different. Okay. You can only compare in the same fluid. Okay, so this is the process. This is the logic behind. Okay. So can you write down, expand this equation in oil first? So they have to share a same coordinate system since this is a problem. So let's say this is a z-axis, start from the bottom. Usually, the rule of thumb, z-axis always start from the lowest point. That will be easy for you to do the calculation. At least one point has 0z, right? That's also a strategy, okay? You can actually specify the origin of z any place, doesn't matter. The result will be the same. But for the convenience, okay, you always want to specify the z on the lowest position of your domain. Then all the z will be positive. I like positive number more than negative number. Okay, so all the z in your problem will be positive. Okay, anybody can help me write down the hydrostatic principle in oil? Pz3 equals to Pz2. Okay, do with me. At the end of this class, everybody remembers. It's in the previous page. Do you still remember what is Pz? Come on. You say it.
Is that just the piezometric pressure?
That's right. Pz3 means piezometric pressure on point 3. Okay, give me the expression for the
P plus gamma Z
Which P?
equals C.
Which P? Now we're talking about the Pz3. So what is Pz3? I want 100% correct expression.
P3 plus gamma oil Z3?
That's 100% correct. I want you to write it down, okay? I'm helping you because in the test, without writing this down, it's more difficult, okay? If you write down the equation correct, then you just substitute values. It won't make a mistake, okay? Is that right? Everybody agree? Piezometric, Pz3, piezometric pressure on 3. The expression is P3 plus gamma oil Z3. I don't care what the Z3 value is there. I will substitute the value later. Don't worry about it, okay? Write down the expression correctly first. That's a point here. This is the gamma oil. Be careful. You are looking at in the oil region between 3 and 2. Both of them are in the oil. So the gamma oil here, okay? So how about the piezometric pressure on point 2? Now it's easy, right? You can follow the same trend. Anybody?
P2 plus gamma oil Z2.
That's correct. You said it in 16 seconds. You know what I mean? They have a 17-second rules. You know, this is education. They have a paper, PhD for education. They have research. They say, statistically speaking, if the teacher waits for 17 seconds, the student will say it. See, that's a science. You did it in 16 seconds. So quiet. I'm just waiting for 17 seconds. Okay, good. Now this is the oil, right? So exactly, that's the equation. Okay, so can you which one is the unknown in this equation?
P2.
Yeah, this is our unknown, right? Okay, so do I know everything else in this equation? If I know everything else, I can solve for P2, right? Look at it. Do I know everything else?
Yes.
Yes.
Okay, we do, right? Good. Any zero here?
P3.
Yeah, this is 0. Okay. So gamma oil, we know it, right? You already did 7A48 Newton per cubic meter. So what is Z3? Be careful. What is Z3? On the surface, a lot of students will say it's 0 quickly without thinking. Yeah, it's 3 meter. Be careful. You're following the origin, following the Z-axis here. In this axis, in this coordinate system, 0, Z is in the bottom. So on the surface, it's not 0. It's 3 meter. Okay, so P2 plus 7A48. What is Z2?
2.1.
2.1 meter. Okay. Okay, now can you calculate the P2 for me?
7,063.2 newtons per meter squared.
7,056, huh?
I got 63.
63, that's fine. Pascal, okay, remember the unit for pressure. It's Newton per meter square, right? We give a name Pascal, okay, by convention, PA. You can convert it into PSI, PSF, you know, if you use English system.
If we put newtons per meter squared on the test, are you going to count off?
That's definitely okay. That means show me that you know what pressure means. But I would suggest use Pascal. That's the convention. When you write Pascal, people knows. Okay, is that good? Now we find the, hey, that's good. I find the interface pressure, right? That's good. Okay, so now our goal is to find the P1 right, in the bottom. So what is, so we use hydrostatic principle in water. So piezometric pressure of 2 equals to piezometric pressure in 1 in water. So that's a 2 piezometric pressure, PZ2 and PZ2 here. This first one is in the oil, okay? It's had different value of the PZ2 in water, okay? Be careful on that. So tell me the expression for the left-hand side of this equation, PZ2 equals to PZ1, so piezometric pressure of 2 in water. What is the expression? Go ahead. I think you knew it.
P2 plus gamma of water, Z2.
That's right. Absolutely right. Okay, so 1.1 piezometric pressure on 1.
And it would just equal P2, right? Because gamma's
No.
Z1
What is the expression for? Follow me. Okay.
plus gamma Z1.
Okay, so P1
Gamma water.
plus gamma water. Yes, you have to say it's water, right? C1. Good. Okay.
And the Z there is equal to 0, right?
Yeah. I will reach that. Let's look at the equation. That's more important to me. More important is write the equation correct before you think about values. Okay. Have this habit. Okay. I have this. I always look at the equation instead of values. Okay. Putting values is computer's job. Okay. Our job is tell computer what to do. Okay. Good. I think this is the correct equation. Now we're putting values. Any 0 here? You said it, right? Z1 is 0. Okay. I guess that's only 0, right? Yeah, be careful. That's only 0. Okay. P2 we calculated already somewhere in here. So now we can put in values. 7063 Pascal plus, what is gamma water? Oh, we have it, 9810 Newton per cubic meter, right? What is Z2? Be careful.
2.1.
Yeah, 2.1. We already used the ones. Equals to P1. Okay, that's it, right? One equation, one unknown. What is the P1? So P1 equals Anybody?
27,664.2 Pascal.
664, right? Pascal. Okay, that's the gauge pressure on the bottom of the tank. Okay, notice the value is smaller than atmosphere, right? Atmospheric pressure is what, 101 kilopascal. Okay, this is 26K only, 27K. So, but this is the gauge pressure. This is 27.6K thousand pascal above the atmospheric pressure. If you want to convert into absolute pressure, it will be 137, right? 137K pascal. Okay, be careful. We are using gauge pressure in most of the cases. Now you know why we use gauge pressure, right? Because look at this 3.3. You have 0 pressure on 3 if you use gauge system. Okay, if you use absolute system, you'd have to put 101,325, 101,325 pascal on 3. Then the whole calculation will be much more complicated. Okay, but turn out to be the same value. Okay, the gauge system, what we use is for the simplicity and the convenience. Okay, it is good. This is still a very simple problems. Okay, but we try to use this hydrostatic principle. Piezometric pressure is the same between 2 points. Okay, to solve this.
So what is the benefit of using that instead of just gamma H? Because you get the same answer as long as you
Yeah, you have to
gamma Y.
Exactly, but gamma H you have to do 2 times. You cannot do gamma the whole 3 meter. You have 2 fluids there. Same thing. This is the gamma H. Look at this equation. This is a gamma P2. Look at this P2 equation. P2 equals to gamma oil times what H? 3 meter minus 2.1. It's 0.9 meter. P2 is gamma oil times the H of oil. And what is P1? P1 is P2 plus gamma water times the H of water. Z2 is the H of water. It's the same way, okay? But you have to do 2 times anyway, right? You cannot just say, hey, a gamma times 3 meter. There are 2 fluids there.
Yeah, so like on a test, we could, if you ask specifically for this one, we'll use the piezometric pressure formula, and then we could check it with the other one or something.
Yeah, you can check with the other one. I want to see the piezometric formula. Okay, but you basically it's the same. You know what? That looks the same, but if you do 2 times.
So was this based off of, did head pressure, the phrase head pressure, I'm familiar with head pressure. Did that come from this or the opposite? Did they come up with this to describe?
Okay, we choose this equation right now to do. Okay, so if you choose this equation to do, everything is called head. This is the pressure head. Okay, pressure head, elevation head. But I think what you said, head pressure is different things, right? It's a static pressure sit on top of a surface or whatever. Is that what you mean? Head pressure or pressure head?
Yeah, we always refer to head to like how much head does a pump have?
Yeah, exactly. That's what I say. Industry always people using head. This is this equation. We can use this equation to solve that problem. Same. Piezometric head is the same between 1, 2, between 2 and 3. Okay, that's exactly the same form. No difference. It's just divided by gamma. Okay, between these two. Okay, you talk about head. It's hey, just like I said it before I solved this. You can even talk about the whole weight. If I know the weight sitting on top of me, I divide by my surface area in the bottom. That's my pressure. Do you agree?
Yeah.
Yeah, it's a different way to solve the problem. But here we are introducing the hydrostatic principle. You use piezometric pressure or piezometric head at the same between 2 points to solve this problem. Okay, this is a 2 fluid problem. Be careful. Okay, you can't just use a one equation. Yeah, yes, you can. I'm going to show you later, next class, how to use a more easy way to do those kind of problems. But here, fundamentally, you cannot directly compare 3 and 1, okay, because there are 2 fluids. You have to go through 2, location 2, okay. Hydrostatic principle only satisfy in a single fluid. Okay, if you have 2 fluids, you have to do 2 times. That's a little difficulty here. It's just 2 fluid problem. Does that make sense?
Yeah, you do. Yeah, you would have to do, if you do it with just rho, it would be rho of oil times 0.9 plus rho, or gamma of oil plus times 0.9 plus gamma of water times 2.1.
Yeah, that's exactly these 2 equations. Look at this. Gamma oil times 0.9. This is P2. Then P2 here. Then plus gamma water times 2.1. Okay. Then this is the pressure on the bottom. Is that right?
Yeah.
Yeah, that's the same thing basically. Okay. I'm just showing you the theoretical background of this coming. Where does this coming from? Gamma H. Since you talk about this, let me see how much time I have. Okay. Okay. Let's just talk about this. Hey, I have a simple procedure here for this problem. P1, P2, P3. You said it here. Okay, P2 is gamma oil times H1. Let's say H1. I don't care what value. Okay, H2. How about that? I like to use letters. H1. H1 is here. I don't know. H oil, how about that? I want a general formula. H water. Okay. Let's say gamma oil, H oil. Is that right? That's from our previous this equation, right? Okay. So how about P1? P1 will be P2 plus gamma water H water. Do you agree? I want to let you get away from numbers. You always think about number values. No, I want you to think about the formula. Okay, that will make you a better engineer. Okay, is that right? Okay, so can you substitute this into P2? What does it look like? P1 equals, actually this is a plus P3, right? I want to make it more general. P3 is 0, right? If you substitute this P2 into the second equation, it will become P3 plus gamma oil, H oil, plus gamma water, H water. Is that right? Okay. That's beautiful. That's kind of like almighty, you know, all kind of application you can just, if you have multiple fluid. Okay, that's actually the equation in the textbook on page 75. It doesn't have the equation number. Page 75. The equation on page 75 is this. P, it said P2, okay, whatever. P2 equals to P1, it's just different numbers, okay. Plus summation, gamma I, H I going down, minus summation gamma J, Hj, then goes up. Okay, so let me explain it to you. Your unknown, you put it as in this equation at the left-hand side. This is your unknown ending point. Right-hand side, this pressure P1 is starting point. Okay, seeing this problem here, P1 is your ending point, P3 is the starting point. That's why P1 equals to P3 plus something, right? Okay, starting pressure, in our case, P3 is 0. Okay, that's why it's gamma OHO plus gamma water HO water. Okay, so what are these? Gamma H, see, you have plus sign and a minus sign here. Okay, so you found the starting point, P1, okay, P3 starting point. So next route is going towards point 2. So the next point, if it's going down, comparing to your starting point, then it's a plus. Okay, you go through from the 3 to 2. That's why it's plus. Then next route, you go to 2 to 1. It's still going down. It's still a plus. Okay, so, but if the next point is going up, okay, for example, I have a case like this. I have a tube. You have multiple fluids in this tube, for example. This is one fluid. This is another fluid. Let's say this is 1. This is 0.2, 0.3, 0.4. Let's say 0.4 open to atmosphere. What is the pressure on 1? Okay. So the simple way is one equation. This is so many fluid there. You know, if you use the traditional way like this, you have to have 3 equations. Okay. Let's say we can follow this equation from the textbook. Every time you going down or going up, it will be plus and minus gamma H. Okay, let's say P1, ending point. P1 is our ending point in this problem. P1 equals to the starting point first, right? Right-hand side is the starting point, P4, which is 0 in this case also, 4 is here. Okay, so your road is go from 4 to 3, then go to 3 to 2, then go to 2 to 1. You see that my arrow? That's your direction from starting point to ending point. So now from 4 to 3, you're going up or going down? Let's do 4 first, then goes to 3, then goes to 2, okay?
Where's 4? Is 4 the last one on the
Yeah,
on the right?
yeah, let's say last one on
It
the
is,
right.
yeah, so you're going up, right?
You're going up, so it's plus or minus? Look at this
Minus.
equation. Yeah,
Minus.
it's minus gamma of this fluid, let's say fluid A, fluid B, fluid C, okay? Gamma A times what? H. This is HA, this distance. The distance between the 2 surfaces, right? So HA, okay? Now I'm at 3. So next stop, go to 3 to 2. 3 to 2 is going up or
Down.
going down? Going down, so it's a plus. So gamma of B times H of B. What is H of B? Between 2 and 3. This is your HB. Okay, my drawing is terrible, but do you follow me? Okay, now I'm at 2, end of the B fluid, right? Now I go to 1. Go up or go down? From 2 to 1.
Up.
Up is what? Minus. Gamma C times HC. HC is the difference between 1 and 2. Okay, you directly use one equation to solve for pressure on the ending point 1. Okay, how beautiful is that? Thanks to your question, actually. I plan to talk about this next class. Okay, so you bring this up, and I think that's a better way, indeed. It's a very complicated problem. Look at this tube. Okay, right? Then we just use one equation. Okay, but you know that equation is derived from the procedure we did in the previous page. Okay, piezometric pressure is the same in one fluid. Piezometric is the same in the other fluid. Okay, you have 3 fluid, you're gonna do this 3 times. But now we just use one equation. Okay. Then you put in the values, whatever values, I don't care. You can calculate the P1. I'm just confident you can calculate the P1. Is that right? Any questions? Since we talked about this, let's look at the example 3.7 in the textbook. Oh, I'm out of page. I'm gonna create a new document. Any questions? Any question before I move on to the new document? Do you remember this? The only thing is the sign. Be careful. When you go down, it's a plus. When it go up, okay, it's a minus. The equation is always gamma, the fluid, times the H, the level difference between 2 ends of the fluid. Okay, so in that sense, hey, my starting point, look at this example we did, right? Starting point is 3, ending point is 1, what we want to calculate. So start from 3, we go down to 2, go down plus gamma oil, H oil. Okay, then we go down again. Again, it's plus gamma water times H water. So one equation, we solved that. Is that good? Okay, let me create a new document. Let's make it 10 page. Okay, do you see the blank paper now? Okay, example 3.7 in the textbook. Okay, you have initially you have a tank. In air on top of this oil tank. Okay, the oil tank go out like this. Okay, so that's the oil surface. So this first part is, of course, it's oil. Okay, so this part is air. Air separates oil with the mercury. Okay, it's a manometer, right? We'll talk about manometer later. This is the mercury. Okay, this is actually a pressure meter. Okay, you try to measure the pressure inside the oil tank. Okay, but you don't want to mix the mercury, the fluid, the measurement fluid, the mercury with the oil. That's why you separate them with air. Okay, so that's a device. Okay, I give you the dimensions. This is, it says point. This is a 0.1, okay. Beginning at the opening here is open to atmosphere. This is L1. This is 0.2. L2 here. This is L3, 0.3, 0.4. Okay. The goal is to calculate the pressure in the tank, the air pressure. How much pressure I need to put in the tank. Okay, what is the pressure in the tank? Okay. Everybody clear with my drawing? Any question on in terms of drawing before I start? Is that good? Okay. So I want you to write down the equation for me. Okay, what is the P4? Okay. So what's the first term in the right-hand side?
Be minus gamma.
No, What is the first term? Answer my question. I want you to stick with the procedure. I'll show you the equation.
P1.
Yeah, first term is the starting point pressure. Although it's 0 in this case, keep it there, okay? Sometimes you will see a problem, it's not 0 in the beginning, okay? So keep it there, okay? It's a good habit. Write the equation complete, okay? If it's 0, it's 0, then you can deal with it later. Okay, starting pressure, do you agree? Okay, so now what's the next term? So you check the next level. Is that going down or going up?
Down.
Going down, so it's plus or minus?
Plus.
Plus what?
Gamma mercury.
Gamma
L1.
mercury times L1, that's correct. Everybody, now we're getting here. My arrow is this, right? Starting to the end, okay? Now I'm at 2. So next stop, 2 to 3, is going up or going down?
Up.
Going up, it should be plus or minus?
Minus.
Minus what?
Gamma air
Yeah.
times L2.
Times L2. Okay, now I'm at 3. Okay, now I'm going from 3 to 4. It's going down, right? So should it be plus or minus?
Plus.
Plus gamma
Plus
oil
gamma oil.
times
P3.
times
L3.
L3. You solve the problem. As an engineer, you write down this. Okay, intern, come do the calculation for me. Okay, that's exactly what we do, right? If you be that position, you probably have people work for you. But you need to tell people the direction, okay? So do I know everything else in the right-hand side? I think I do. Okay, let me give you the value L1, L2, L3. It said in the textbook, it said L1 equals 40 centimeter. L2 is 100 centimeter. L3 is 80 centimeter. Okay, I got everything I need. Okay, gamma mercury is, S mercury is 13.6. Oil, let's see, oil is still 0.8. S oil is 0.8. Okay, some calculations here. So let's do it. How many minutes? I have 6 minutes, more than enough. P1, what is P1? 1 by 1. We know everything on the right-hand side, right? Open to atmosphere at 0. Okay, so what is gamma mercury? Give me an expression here in terms of S. You have to remember this, how to calculate the property gammas based on specific gravity, right? What is gamma mercury? Give me an expression with numbers.
Is it 133,416?
No, yeah, you're probably right, but I need an expression. I don't like final numbers before I see this expression. If you write this down.
Oh, that's the gamma of water times S of mercury.
That's right. You know why I need to write this? 10 years later, people may come back to sue you. Then I go back to my original writing. Oh, I know that's what I did. It should be right. That's your evidence, your proof, okay? Write it down. Before you just write down the final number, then you don't know how I get this, okay? At least this part is right. Maybe the intern did the calculation wrong later. It's not your responsibility then. Okay, L1, what is L1?
40 centimeters.
What
so
number you should put it in here?
0.4 meters.
0.4 meter, that's correct. You have to do meter, okay? it confuses you with give you a centimeter, but put meter in the equation. Just like in English unit, you always do PSF, okay? Don't put the PSI in the equation, it's wrong, okay? What is gamma of air? It didn't say, it's kind of like tiny. Gamma air is about the raw air is about 1 kilogram per cubic meter. Water is 1,000, so it's like 1,000th. So can we just say 9.8 Newton per cubic meter times L2. L2 is 1 meter, okay? Then plus, what is gamma oil? 0.8 times 9810 times 0.8. See, I'm just substituting the numbers. If my equation is right, I'm very relaxed, okay? Just putting numbers there, you know, it's guaranteed you have a good answer. As an engineer, you have to guarantee your client, your calculations right. Otherwise, people's livelihood, whatever, rely on you. Okay, so you see, I want to convey this idea. It's a serious job. You have to make sure it's correct. It's not like I want to make sure it's correct. You can't sometimes if you don't follow a correct procedure. If you follow a correct procedure, likely it will ensure your correctness. Okay, I know you know a lot of information here. You want to jump to a number or whatever. Don't. Okay, follow the procedure and ensure the correctness. Okay, so now I think I have everything in the right hand side. So P4, you can now key in calculator to find the P4. What is the value?
59,635 Pascal.
59,300, you say? 35?
635.
635 Pascal. Okay, is that what everybody got? Well, I see a little different result in the textbook. I see a little bit more than what you got. I see 100.
That's what I got.
That's also what you got? Well, maybe that's something
Yeah,
wrong.
59,630.
Okay, let's see. The equation from the textbook is exactly same. 13.6 times 9810 times 0.000. Okay. So we're right. We have in the book it said this is L1, this is L2, this is L3. So L1 and L3 are switched. So you're right. Okay, correct answer. Okay, so this is different with the book. Okay, the book is L1 is in the left, L3 is in the right. Okay, so if you switch that number, then you will have about 110,000 Pascal gauge. Okay, is that good? Okay, see, we make a very complicated problem. We use a very a shortcut. Okay, very smart procedures. Then we can actually solve this type of hydrostatic problem. Okay, but as you know, this is derived. This equation, this is nice little one equation. It's derived from the hydrostatic principle between single fluid. You have the same piezometric pressure. You know, so based on that. Okay. Okay. I guess that's it. Good timing. 10:45. See, perfect timing.
So
Okay.
in the equation that we talked about right before the example, the Z is just denoting, which way is up or down.
No, Z is your coordinate system. In that equation,
Yeah,
the equation is in terms
that's what
of
I meant.
yeah. In terms of the coordinates. So you have to have a fixed coordinate origin. Zero Z. Based on that 0Z, you have relative Z's, right? You have different Z coordinates. Okay, I guess that's it for today. I will start to assign homework problem for chapter 3. Seems like we We didn't, of course, we didn't finish. I don't want to wait. Chapter 3 is so long. I don't want to wait to finish chapter 3 to assign homework. So I will assign the first set homework, okay, today after the class. Then start to, before you forget, start to, maybe practice
So
a little bit.
is homework still not going to be for any kind of grade?
No. You don't need to submit homework. It's for your benefit. For you to practice and prepare for the quiz.
Okay.
Okay, so have a good rest of the day. See you next week. Today is Thursday, right? Yeah, almost weekend. Have fun.